Thank you very much, James, and thank you, President Grimson, and for the Icelandic host. It's wonderful to be back here again. As you have heard, I'm a long-term monitoring program, so I answer some of James' problems. It is extremely important to have a long-term view of the Arctic. What I will try to do is focus on the Arctic landscape in transition. You have seen this slide before. You saw a modern version. This was the classic originator of that slide, showing dramatic changes in the last 250 years in many societally relevant factors. Of course, in the Arctic, we have amplification of those factors, and you've heard that too. This is a graphic that shows temperature changes over the last 30 years from the South Pole all the way to the North Pole. Even though there are data gaps in that graphic, you can see the dramatic amplification of climate change in the Arctic. What does that mean? Well, the first impact of climate change in the Arctic is on the cryosphere, the frozen part of the planet, the ice and snow. If we look at the Greenland ice sheet, the second biggest ice sheet in the world, second only to Antarctica, we see in 2012, on the 12th of July, a record surface melt of 97% of the Greenland ice sheet. We thought that the Greenland ice sheet was stable 20 years ago. It is not. We've also lost volume of the Greenland ice sheet, and here you see losses in terms of gigatons over that period. As well as the Greenland ice sheet, we have ice on land in the form of glaciers. And in every Arctic country, and many alpine countries, you can see the dramatic changes in glacier mass balance, glacier volume, glacier extent. Here you see photographs from 1941 and 2004. To the right, you see the place where we were climbing mountains this summer, with trees moving into this environment almost before the ice has gone. The changes are dramatic. In the Russian Arctic, 20 to 50% of all the glacier volume has been lost since 1972. That means that my grandkids will be lucky to see a glacier in the Russian Arctic when they're my age. The cryosphere also extends to the lakes and the rivers, and lake ice is becoming thinner, like the sea ice. It's also becoming a lower duration, and that has dramatic consequences for the isolation of communities and the operation of extractive industries in the Arctic that have depended on ice roads for many years. And of course, the traditional lifestyles of the indigenous peoples depended on transport with reindeer sledges and so on for thousands of years. Also importantly, the water resources of the Arctic are somewhat at risk because when the ice cover of the lakes moves, then the water evaporates. So we're seeing a lowering of water levels in the Arctic and a disappearance of tundra ponds in many areas. Although permafrost isn't per se ice, it's simply frozen ground, we're also seeing a warming of the permafrost throughout the Arctic. The graphic shows, again, about a 30-year monitoring program from borehole temperatures of permafrost in different places of the Arctic. They are all warming. And the active layer above the permafrost is thickening. The consequences of that are drying of ponds, again, a second mechanism to get rid of water in the Arctic, as the water drains through the permafrost, where the permafrost was. A combination of bad engineering and permafrost thaw, where there is ice-rich ground, leads to subsidence, and it also leads to subsidence in natural environments. So you see here Polsa mires, mounds of permafrost, collapsing and forming new ponds. Snow cover extent is also decreasing. The snow-free period has increased by about 2 weeks over the last 30 years, and most of this is happening in spring because of a positive feedback to the climate system through warming affecting the snow and the disappearance of the snow reflecting less radiation back into the atmosphere. It's a positive feedback which is amplifying and accelerating. Not only is the extent of the snow changing, the actual characteristics of the snowpack are changing. And the red lines on this graphic is a monitoring program for 50 years in the subarctic. Each red line represents a thaw event in the middle of winter. This is the Arctic without snow in the middle of winter. And once we have those ice layers, animals can't live under the snow like lemmings, and reindeer that depend on digging through the snow for vegetation die. And we have lost millions if not tens of millions of animals over the past 20 or 30 years. The Arctic, as you heard from Jane, contains a vast reserve of carbon in the soils and on the continental shelves, which used to be tundra ecosystems when the sea level was lower. The graphic on the left shows a map of the carbon concentration in the first meter of soil throughout the whole of the Arctic. The middle graphic shows the situation in parts of Siberia, this is the New Siberian Islands, where the devastation of the permafrost thaw and the formation of vegetation-less tundra is leading to gaseous carbon going into the atmosphere through carbon dioxide, particulate carbon being blown onto the sea ice, which melts the sea ice faster, and carbon flowing down the river, the little stream you can see there, into the Arctic Ocean, taking carbon with it. Where the land is dry, as in the middle photograph, carbon dioxide is generated by a warming soil and faster operating microbes. Where the land is wet, you get an evolution of methane, which is 30 times about more potent as a greenhouse gas than carbon dioxide. It's dangerous to smoke in the Arctic. That is one important feedback from terrestrial landscapes to the Arctic. There is another important feedback that I already mentioned. It's called albedo. It's the reflectivity of the surface. And that reflectivity of the surface is changed when vegetation moves into the snow and sticks up above the snow surface. And it's also changed as the snow season decreases in spring and more radiation is absorbed by the land surface. That is another way the Arctic is leading to a warming of the rest of the world. Another way is there is an increase in forest fires and forest pest outbreaks and even tundra fires. Tundra should be wet, it should not catch fire. But in the middle graphic at the bottom there, you see a fire on the north slope of Alaska in 2007. In a few weeks, the equivalent of 50 years of carbon accumulation was dispersed into the atmosphere as a greenhouse gas. Just in a few weeks, 50 years of carbon concentration. And then on the bottom right, we have the industries, the dirty industries that are producing plumes of black carbon which reach out to Svalbard and to northeast Greenland. If we now look at the tundra ecosystems of vegetation, we can look from space, as Barbara Ryan described earlier this morning, and we can identify change. And we are extremely surprised. This is called the greening of the Arctic, and Jane introduced that term to you, but only 37% of the Arctic's land surface has actually greened. That's much less than half. Why? We don't know. But one possibility is that forget the long-term trends that everyone has talked about and think in terms of the short-term events. These events are the tundra fires. The events are the outbreaks of insect pests, the snow melting in the middle of winter, the rain on snow events. All those destroy the possibilities for herbivores to be active. The absence of herbivores allows vegetation to increase in growth. So we really don't know why the vegetation is greening, and we don't know why it's not greening in the areas that are not changing. What is Britain doing? Well, it's involved in every one of those stories that I've described to you. But also, through the leadership of a big international program that involves over 20 countries, we are pulling together research stations throughout the whole Arctic. And Jane mentioned a need for observation data. We are doing that. We link 71 research stations throughout the Arctic. 3 of them are here in Iceland. The last one from Iceland joined 2 days ago when I landed at Keflavik. Together, these 71 research stations hosted this year 5,100 scientists. And they host and facilitate 76 international networks. They cover all topics, and for the first time ever, they are working together. Through my Finnish colleagues, we operate a transnational access program with funding from Canada, the US, and the EU to allow scientists to go to different countries than those that they work in. And here you see a sort of flight schedule for groups from around Europe who are going into the Arctic. And in terms of the biggest group that we are funding is the British group. We have put 67 UK research groups into the Arctic in the last 4 years. That's 147 researchers. And they come from 30 UK universities and 2 institutes. And they visited 16 research stations in every Arctic country. And of course, they collaborate with the scientists at those research stations and in all those countries. I can't hope to give you a breakdown of the types of projects, but I can read a few headlines. Glacier monitoring. You saw the importance of the disappearance of glaciers, the thawing of the Greenland ice sheet. British scientists are there, working in southeast Greenland, for example, tracking the changes. You heard about albedo, the reflectivity of the snow. Here, British scientists have pioneered the growth of organisms in snow and ice. Here you see 3 different types of snow, each with microbes in there affecting the reflectivity of the snow and ice, leading to a faster melt of the snow. Biodiversity, we are covering that too. To conclude, the abiotic changes, the cryosphere changes, and the climate changes, they are dramatic. There's no discussion about that. The biotic changes, they're not. They vary from dramatic to counterintuitive to no change at all. And we don't often understand why. What is important, and you've heard little about so far, is that local factors and extreme events often override the long-term trends. So prediction is incredibly difficult. Our models don't hold that potential yet. And everyone will be affected by climate change in some way. To summarize what UK researchers have done, they continue to play an extremely significant role through education. There are professors educated in Britain in every Arctic countries. Through expeditions, schoolboy expeditions, undergraduate expeditions have gone to Svalbard, here to Iceland very frequently. Research, innovation and leadership, interactors led by British scientists. Coordination, assessments, the Arctic Climate Impact Assessment, the Sweeper Assessment, IPCC, and so on. And the photograph to finish with is a photograph of Svalbard, and this is taken in 1936, and it explains the word legacy. Not only did Britain pioneer some of the science in many parts of the Arctic, the data created 70, 80, even 100 years ago by British scientists is being revisited today to look at how these systems have changed. That is a different type of legacy than educating professors in the Arctic, but it's nevertheless extremely important. Thank you for your attention.